Okay, today we're going to talk about peak demand forecasting, and this is an application of linear regression. So I want to set the stage a little bit in terms of why we think about peak load forecasting as something that's important that utilities should do, with putting that in the context of the other objectives, or the main objectives that electric utilities have. And the first is, of course, reliability. So we need electric utilities without fail to constantly balance supply and demand. And the other objective is to do this at the lowest possible cost. And you can argue a million different ways which model is best for getting high reliability and low cost, but those are the two main objectives, and to those two objectives we've now in the last 20 or 30 years really added a third, and that is environmental sustainability, with most attention going towards making sure that the electric power sector is a low emitter or zero emitter of greenhouse gas emissions. So ensuring reliability, and that's mostly what we're going to talk about today, is really a multi-scale challenge. You have to balance supply and demand of electricity on a second-to-second basis, on a minute-to-minute basis, hour-to-hour, daily, seasonal, and all the way up through multiple years and decades. And there are different logistical challenges that come into play when you're trying to meet electricity demand on each of these different time scales. The need to balance supply and demand on a second-to-second and minute-to-minute basis is really tied to, and when I mean meeting supply and demand, I'm not talking about contingencies where you lose a power plant, or you lose a transmission line, and all of a sudden your supply has decreased dramatically, and all of a sudden you have to replace it with something else. That sort of situations that we plan to have, but we don't consider to be normal operations. But there are elements of the normal operations of power systems that do require active dynamic management on a minute-to-minute and second-to-second basis, and that's particularly related to what we call frequency regulation. So if you recall from the lecture on the Grid 101, we talked about why we have AC power systems in the United States, and we talked a little bit about the mathematics of AC power and AC power flow. And so you should realize that the supply of electricity is this constantly fluctuating value, and the way in which it fluctuates, the rate at which it fluctuates, is the frequency. And so different power systems have different frequencies. So in the United States, everything operates at 60 hertz. In Europe and maybe Asia, I think it's 50 hertz. So the entire US AC power system is all operating at the same frequency, 60 hertz. Now, if you do not balance demand and supply perfectly, the frequency can increase or decrease. If demand is greater than supply, frequency increases. If demand is lower than supply, frequency decreases. And so you have to constantly adjust the availability of electricity, the supply, to match it to demand within a certain range, in order to keep frequency close to 60 hertz. And if you deviate far enough away from 60 hertz, then you can have grid scale failures. So on the bottom right figure here gives you a sense of scale. So if you, on the left axis, you have total load or demand that a utility would see, and on the x-axis you have time of day. And so the solid blue line is sort of smoothed electricity demand, and maybe aggregated to a 15-minute or 5-minute basis or hourly basis or something. The green line is what the utility actually sees on a minute-to-minute basis, and you can see that demand for electricity fluctuates around the smooth blue line in sort of a noisy fashion, and that noise, if you blow it up and look at it, is what you get in the red plot below. So the red plot shows you deviation around zero, and that corresponds to the second right y-axis. And so the red tells you how much generation a utility has to increase or decrease in order to keep this frequency at 60 hertz. And most generators do this automatically now. They have what we call automatic governor control. And so many power plants can receive a signal like this from the utility and automatically adjust their output in order to perfectly balance demand and supply on very, very small scales like this. So we also need generators to balance demand and supply on an hour-to-hour basis, and we've talked a lot about that already. This is the whole idea of electricity demand fluctuating throughout the day because of temperature, because of economic activity, because of other human behavior. And we require generators to respond to those types of changes in demand and produce what we need. So it's sort of I always find it funny how people, lay people, I think, have this perception that electricity generation is sort of out there, and then we go decide how much of it we want to use. When it's really the opposite. Our demand is there, and then the generators have to perfectly respond to that demand in real time. And so on the left plot here shows the difference in shape between summer and winter electricity demand profiles. And I'm indicating here that the main driver of the shape of these profiles are heating and cooling requirements. And then the right plot here shows another figure we've seen before, which is probably peak electricity demand, but as it changes throughout the year. And you can see looks like there's 3 years of data shown here, and you have two main peak periods of the year, winter and summer, with the bigger peak period occurring in the summer, and then two valleys. So in the spring and in the fall, electricity demand is fairly low. So again, we're requiring electricity producers to operate their generators in a way that makes sure that not only do we have electricity demand available on a minute-to-minute, hour-to-hour basis, but also that it's available during the right periods of the year as well. So what's left here? We're talking about everything that happens within a year. But there is, another significant challenge that utilities face in ensuring system reliability, and that is trying to figure out how much capacity, how much generation they're going to need on a day-to-day or even seasonal basis. But from year to year, how do you account for long-term changes in electricity demand that might require you to build more power plants? And this is a really difficult, probably more difficult than any of the other issues we've raised so far. This is a difficult challenge for utilities, and because there's so much uncertainty going out into the future, and the further you get out into the future about what electricity demand is going to be, and the cost of either underestimating that or overestimating it are substantial. And so you have to do this, and it would be a little easier if it only took 6 months to build a power plant. But the reality is that the logistical, challenge of building a power plant, as well as the regulatory process of getting that approved and the permitted and borrowing the money, etc., it can take years and years. And so utilities have to start really early, many years in advance before they build a power plant. And that means that they have to be able to predict or forecast pretty far out into the future what they think electricity demand is going to look like. And that's what we're going to talk about today. So typically what a power utility will look at when they're trying to project demand out into the future and project the need for potentially more or additional capacity is what peak annual load is. Because the concern here is that if you're thinking about building new capacity into the system, what's the metric that we would use to figure out if a system is going to have enough capacity or if it's going to be reliable? Well, an easy one, it can get more complicated than this, but an easy metric we would use is whether it's able to meet demand in the highest or peak demand period, peak demand hour or day of the entire year. So what we're saying here implicitly is that if we design a system with enough generating capacity so that during the hottest day during the summer we can meet electricity demand, then we're basically assuming that every other period of the year will be fine as well. And so this figure at the bottom right, I've sort of identified here with the red arrows what the peak annual load or demand is for each of these years. So, a key element of system planning in most power systems is, number one, a diversity of resources. And part of that's because, you have different levels of flexibility with different types of generation. And so meeting electricity demand that constantly changes on an hour-to-hour, week-to-week seasonal basis requires some resources, at least some, that are flexible. And, it can be too costly to have all resources that are super flexible. So we try to have a balance where we have some that are, cheap but not flexible, like coal and nuclear, and then others that are flexible and might be a little more expensive, like natural gas. The other really key element in system planning is redundancy, right? So, this is a pretty pronounced constant trade-off in not just electric power systems, but infrastructure planning and engineering in general, right? There's a cost trade-off. By increasing redundancy, you are potentially increasing reliability, but also increasing costs. In other words, we could build twice as many generators as we need and have a much smaller likelihood that we're going to ever realize some sort of shortfall in electricity demand and potentially blackouts or something like that. It's a little more complicated than that, but we have to try to figure out, is it worth it for us to do that? Because building twice as many power plants as we really need would be extremely expensive. And so one of the challenges for not only utilities but regulators that oversee the operation of utilities is trying to figure out exactly how much redundancy we actually need and balancing that trade-off between cost and reliability. So, and this is just pointing out the part of the variable cost versus flexibility trade-off I just pointed out. We need some types of generation that are more flexible, and in general, those tend to be the more expensive types of generation, especially if you're talking about natural gas. Not many utilities use oil at this point. Hydro is, of course, extremely expensive, but it's very geographical in its availability, right? So certain types of the U.S., certain areas of the U.S. have a lot of hydropower availability, but those are the parts of the U.S. that are naturally sort of blessed with good places to build hydroelectric dams. Not many places in the U.S. rely on hydro for more than about 6 or 8% of generation. So on the y-axis here, you have the marginal variable cost of producing electricity per unit of electricity. And then on the x-axis here, the cumulative amount of electricity that any one system could produce. And so this is what we would call the marginal cost or system supply curve. And I think this is for Dominion or Duke Energy. But this is more or less what a lot of the U.S. looks like. You have most of the generation being provided. Most of the x-axis is coal or nuclear. And then some natural gas and a little bit of oil, but oil is so expensive that you really are not turning that stuff on until you really have to. So again, here we have that same portfolio of coal, natural gas, nuclear, although hydro is not listed here. These are just thermal power plants, and I've indicated off to the left here whether we would consider them base load or peaking, and there's sort of an intermediate category here too. Shoulder power plants would be ones that can ramp up a little bit but don't ramp up enough to be considered peaking power plants. I've distinguished them here by fuel type, so coal, combustion turbine, natural gas, nuclear, and oil, as well as installed capacity. And you can see that the really big plants tend to be base load, and also capacity factor. And we've talked a little bit about capacity factor in the future. It's basically the fraction of the amount of installed capacity that ends up getting used throughout the year. So the highest capacity factor you could have is a 1. The lowest would be 0. And if you have a number that's closer to 1, that means you are on average being used more throughout the year. So we have 2 nuclear power plants, or 3 nuclear power plants listed here, and they have capacity factors of 0.88 and 0.9. So another way of thinking about that is that for each of these nuclear power plants, you could assume that they're online every hour of every day, but just producing 90% of what they could. In reality, they're probably producing close to 100% of what they could all the time, and then there are certain days of the year when they're just completely offline in order to do maintenance. And you can see other types of power plants have much lower capacity factors, especially peaking power plants. The combustion turbine natural gas plants all have capacity factors that are less than or equal to 0.06. So 6% of all possible, generation they could produce throughout the year, they're actually producing. So that gives you an idea of this idea that we have a lot of power plants that we build, but we build them and knowing full well we are not going to use them very often. And that's the redundancy I'm talking about. When it's helpful for ensuring reliability, but when you're moving from 75 to 80% reliability, and then 80 to 85, and 95 to 99, and 99 to 100, each incremental increase in reliability can cost you more because it's requiring you to build more and more redundancy into the system. So some redundancy is preferable, but too much, building capacity in to protect against, a 1 in 1,000 or 1 in 1 million, event. An event that has a really low probability but would still be costly. Actually trying to protect against that can be too much trouble than it's worth if it causes you to build so much capacity into the system that the other 99.9% of the time, all your customers are paying way more than they should for electricity because you've decided to build way more power plants than you actually need. So system planners try to come up with a standard for how much redundancy in terms of generation capacity should be built into power systems, and they do this by using what's called a reserve margin, which is usually around 15%. And reserve margin is the difference between the total available capacity minus the peak annual load, right? So that's how much capacity is left over after you've met peak annual load divided by peak annual load. And we want that to be around 15%. Okay, so now that you know a little bit more about the the multi-scale challenge of meeting electricity demand and ensuring reliability, we can talk about the long-term system. We can zero in a little bit on longer-term, not system planning necessarily, but we're just talking today about load forecasting. We'll talk another day about system planning and how to choose, among a menu of choices about what type of generation you could build, how do you choose which one to build? So today we're just talking about load forecasting, so looking out into the future, out into the future, not next week, not next year, 5 years from now, and trying to predict what electricity demand is going to be like so we can start thinking about, do we even need to build a power plant today? So we're going to take, the example today is going to be taken specifically from some literature that's published by PJM, and most utilities will put out and publish the methodology of how they are thinking about and predicting or forecasting peak annual load into the future. And that, they have to do this. They have to make those sort of calculations public because those calculations are the justification for them asking utility commissions for approval, public utility commissions, for approval to build more power plants, which impacts all of us. It impacts how much we're going to pay for electricity. It can, in some cases, impact greenhouse gas impacts. So this is a fairly transparent process compared to a lot of other aspects of the operations of utilities that are private companies may be sort of shrouded in mystery or proprietary, but load forecasting tends to be one of the more transparent aspects of their operations. And so this is a map of PJM, which is a large wholesale electricity market, and ISO RTO, which is made up of lots of individual utilities. And all those individual utilities have different colors here. So each of those different colors we call an electric distribution company, so an EDC for short. And each EDC that participates in PJM every year is legally obligated, in order to participate in the wholesale market, to provide the following hourly data. Net interchange, so that's the net of all generation that's imported minus all the generation that's exported out of each one of those individually colored areas. And this can be positive or negative. It would be positive if you're mostly importing, and it would be negative if you're mostly exporting. And then internal generation, so the sum of all the generation produced within each individual control area, and then transmission losses. And so we calculate the total electricity load for each EDC, and each hour is the net interchange plus internal generation plus transmission losses, right? That's the total amount of generation you need to produce in order to meet electricity demand, internal to each of those individually colored EDC areas. So once PJM gets that information from each utility, it then starts to initiate a load forecast model. And so they look 15 years out into the future on a monthly basis. They're trying to produce forecasts for electricity demand for each of the individual EDCs and the entire system, or ISO RTO, as a whole. And the key modeling parameters, if you're looking 15 years out into the future, you have to think about what the trends are going to be in equipment and appliance usage, right? So are we adding things as consumers to our lives that use more electricity? Are we replacing older things with newer things that use less electricity? Anticipated economic growth. Are we going to be shifting our use of electricity towards different types of industry, or more industry overall, or less industry? And historical weather patterns as well. What do we anticipate summers looking like 15 years from now, or winters? What do they look like over the last 20 years? Is that a reasonable approximation for what's going to happen in the future? Like maybe yes, maybe no. And so all of these parameters go into a multiple regression model where we have y is our forecast of what the load is going to be or demand is going to be in the future. And this is based off of the relationship, the linear relationship, with a number of different independent variables, all the x's, and then a bunch of different coefficients that we calculate, and that's the goal of regression here, is to calculate all the b coefficients that when you multiply them by all our independent variables, the x's, give us the most accurate possible estimate of y, which is the forecast demand in the future. So let's go through some of the dependent variables in this regression equation. The first would be actual load, right? So actual historical metered electricity demand. And then we'd have maybe expected changes in distributed generation, so something that would potentially decrease load out into the future. Calendar effects, and these are treated as binary 0-1 variables, so if you're trying to predict what electricity demand out in the future is going to be on Super Bowl Sunday, you'd have a specific dependent variable for Super Bowl Sunday, 1 yes, 0 no, but this could also apply to days of the week, holidays, month of the year, weather data, so degree days, but also wind speed adjusted temperature. So the weather data is often included in a format that we call splines, right? So splines are numerical functions that are really like piecewise, not linear, but piecewise functions defined by polynomials, right? So mathematical models that have exponents, right? In this case, we have at the bottom left here a spline, and this isn't specific to any type of weather data here. It's just an example of how you would form a spline. And so you have these different polynomial segments, which are black, and they're all defined for ranges of some sort of value on the x-axis here that we are marking at intervals by these nodes 1 through 6, right? So between 0 and 1 we have not a polynomial, just a regular line segment, right? So we might have this whole function that says if x is between 0 and 1, then y is equal to, in this case, some sort of constant. We'd have another function that says else if x is between 1 and 2 here, then the value of y is described by some sort of polynomial. It looks like a quadratic. And then if x is between 2 and 3, then we're going to describe it a slightly different way. It looks like a different parabola. And then between 3 and 4, 4 and 5, and 5 and 6, they each have their individual equation that, based on the value of x, gives you some value of y. And so often, in order to parameterize these models, utilities find that breaking up the relationship between a certain dependent variable, in this case like weather, the combination of temperature and wind speed, or temperature and humidity, and electricity demand, works best if you have these piecewise polynomial functions called splines. And so an example here would be they might figure out, and this isn't based on, obviously it has some physical underpinning that ties the relationship of weather to electricity demand in different ways for different segments, but mostly this is something that's fit, right, empirically. You say, like, we have all this data and we have this model that we think's right, how should we break up the relationship between winter weather and electricity demand so that our model fits the best? And in this case, we're saying that as long as wind is above 10 miles per hour, then whatever winter weather parameter, dependent variable, we have in our regression is equal to the dry bulb temperature minus the quantity 0.5 times the wind speed minus 10, right? But if wind is not greater than 10 miles per hour, then the winter weather parameter just equals the dry bulb temperature, right? So what this is basically saying that is, if wind speed is above 10 miles per hour, then we want it to have some effect on the winter weather parameter, but otherwise we're just going to ignore it. And we can do the same thing with the summer temperature parameter with regard to humidity here. So as long as the dry bulb temperature is above, and this looks like it's temperature activated, if the dry bulb temperature is greater than 58 degrees, then we do want humidity, which is HUM here, to have some impact on the summer weather parameter that we're including as a dependent variable in the regression. Otherwise, if the dry bulb temperature is less than or less than 58 degrees, then we're not really incorporating humidity at all. So these are all the dependent variables that we're thinking are going to go into the regression. And we can add one more here, and that is economic and demographic drivers. And this is one that can be difficult to predict. In some regions, in other regions, utilities may have more success. So, a lot of this, it's sort of like garbage in, garbage out, right? So if you're using a lot of information that really doesn't mean much in terms of being able to predict the future, then the success of your model is going to be pretty uncertain, right? And if you're talking about macroeconomic prediction, I think the rule of thumb probably is that forecasts are generally bad. We can sort of explain things in hindsight, but predicting how employment's going to change in the future or the economy at large, really, and all, how industries are going to change, population projections, GDP growth, etc. All of that is highly uncertain. But for today's lecture, we're going to assume that there's a little more certainty around those projections. But these would all be things that would be considered good indicators for long-term electricity demand growth. So all of these economic indices, whether it's GDP or population growth, stuff like that, all gets put into this formula for just a composite economic index that represents just the macroeconomic conditions in a given region of the country. And again, so this is all, you have different variables here. You can pick out GDP and population and stuff like that. And all of these are broken up by year and month, and they're proportional to some sort of baseline, and then they're all raised to some sort of exponent. And all of these are, this economic index is probably fit to historical data based on some sort of regression, right? So, how important each one of these individual components of the economic index is itself this other separate model that has probably already been fit before. So those are all the dependent variables plus economic and demographic index. And then the last one, I think this is the last one, is end-use trends and efficiency of appliances. Load adjustment, industrial closing. So changes in industry. You know, in many cases, if you're talking about a small enough part of the country or a small enough control area, if it's just like half of North Carolina, right? If you had a couple really, really big manufacturers leave, that might have a noticeable impact on your demand projections into the future. Okay, so if we have all this information, the way we fit a regression to it is first by fitting this model or training the model to historical data, right? So that what that means is that we have a historical record of all these X values, all these independent variables. We have a record of, weather data and economic data and appliance usage and trends and stuff like that. And on the Y side, we have a record of Y variables, right? We have a record of historical electricity demand data, and then we can use it to make find the values of B that, in combination with all our historical X's, do the best job at predicting Y electricity demand. So for each PGM zone, we end up with a distribution, right? So not one single guess, but a distribution of peak load forecasts using Monte Carlo simulation. And so this is a process, we've talked a little bit about it before in terms of using random number generators and simulating samples from a distribution, a probability distribution. And we'll talk a little bit more about Monte Carlo methods in another lecture as well when we talk about stochastic simulation. But Monte Carlo simulation in general is useful for simulating a phenomenon that has a lot of uncertainty with regard to one or more of its driving influences. In this case, pretty much everything we talked about in that regression is uncertain, but we're just going to leave it at weather, right? Because I think the reality is, yes, population growth, GDP are all uncertain. But I think the degree to which they can be uncertain on a year-to-year basis gives you much less of a swing in what peak demand is going to be, right? So even if when we experienced the Great Recession, right, 2008 and 2009, electricity demand for sure slowed down, and in some parts of the country even decreased. But it wasn't like it, decreased by 25%. When you're talking about uncertainty in weather, right, temperatures on a year-to-year basis, and how that could impact peak demand for a given year, you are talking about uncertainty that's orders of magnitude greater, right? The difference between a mild and a really hot summer in terms of peak electricity demand can be thousands of megawatts. And so that's why we use Monte Carlo simulation here, to put some uncertainty around our guess of what the electricity demand in the future is going to be, due specifically to year-to-year variability in weather, right? And so the first step of this is to, number one, fit a distribution via maximum likelihood around whatever weather parameter we're thinking about, right? And so, for example, you could have normalized dry bulb temperatures in December. If you're just trying to do a regression of what peak electricity demand in December is going to be, you could say, we're pretty sure we know what the GDP is going to be. We're pretty sure we know what population growth and what appliances people are going to be using. But we don't know what the temperature in December is going to be like. But we do know that over the last 20 years, we have all this data about what temperature is going to be in December. And we can put all that data together and come up with a probability distribution. So something that has a mean and a variance. And then we can sample randomly in step 2 from that distribution to get a bunch of different possible values of temperature in December, which we can put into our model, into our linear regression. And when we do that, then we get a distribution of possible December electricity demand as well. So, Any issue with this? Any issue potentially with using a historical distribution of weather data to build probability distributions for Monte Carlo sampling in load forecasting? Well, the obvious one is, of course, climate change, right? So what climate change is doing is literally changing the underlying true distribution of weather data, right? In a way that we don't really know, right? And so that's a big challenge with incorporating climate data into all sorts of industries, is we don't actually know what the true distribution is at any given point, because we don't have a record of that. We're building our understanding of our probabilistic understanding of what weather data does based on the historical record. But if the future isn't going to look like the past, and we might have a guess about how it could change, but that adds even more uncertainty to this. So again, here we're saying that, while this isn't strictly true, we're saying that economic growth we can describe no matter what the value is. We put it into our x value, and it's a one guess, or we're going to assume that economic growth is a certain percentage, and calendar effects and load adjustment, end use trends. We're pretty sure about all that stuff. What we know can really vary on a year-to-year basis is weather, and so this one variable, independent variable x5. Now the coefficients aren't changing. All the b values we fit to historical data, right? That's what came out of the regression. Once we have the model, which is really just our coefficients, then we're plugging in guesses, right? We're plugging in independent variable x's. And again, we're just using single x values for everything except for weather, and then for weather we're using a bunch of different forecasts that we sample from a Monte Carlo distribution. So that ends up giving us, the regression model doesn't have to give you just one value, right? It gives you this whole distribution, right? A probability that load in the future, 5 or 10 years from now, is going to be a certain level, right? Or peak load in the summertime. Now, a related issue, and this is a little more esoteric, that doesn't matter as much in terms of peak load forecasting, but this is a useful process that's sort of related, and this weather normalization, right? So if you're PJM and you're a big ISO RTO, and you're trying to figure out how much capacity every individual sort of utility constituent in your larger system should be adding every year in order to guarantee that there's enough reliability, or to figure out what share of the transmission system on average different utilities are using, because a lot of the cost of maintaining those systems is sort of divvied up proportional to how much electricity each individual region is consuming. It's important to normalize that information for weather, right? Because you don't want to just take like last year's data, right? Because some regions might have had an exceptionally warm year, or some regions might have had an exceptionally cold year, or everybody had a cold year, or everybody had a hot year, and you're not just trying to figure out what on average the whole system consumes in a normal year. You're trying to figure out for each individual system component what the normal electricity demand would be in an average weather year. And so you have to sort of work backwards. The information you already have is what actual electricity demand everybody had, or what actual generation people produced. But that's embedded in that information is what the weather was, right? And so we're now trying to take the weather data out and just get what the average electricity generation or demand would be, in order to get a sort of a static snapshot in a normal year of what everybody uses, in order to allocate mostly just fixed costs. So to do this, you take daily peak loads for non-holiday weekdays over the most recent 3-year period, and you regress that against some sort of seasonal weather variable. So here you have the dependent variable, which is y, which is daily peak load. The x here is some sort of appropriate weather variable, whether it's summer or winter. And then b is the coefficient. This is what we're trying to find. And so once we find that b coefficient, then we can say, well, the normalized peak load for each of these individual areas, we're going to keep the coefficient, but we're going to assume that the x is just at its average point over the last 3 years, right? Or we could do longer than 3 years. We could say 5 or 10 years. And so these average values are then used to assign each individual member utility a proportional share of the system's total capacity requirement. And so this is basically how a lot of different fixed costs gets divvied up. And so it's providing enough cell phone generation capacity. It's the marker that PJM uses to tell individual utilities, like, look, you need to build more capacity or pay somebody else to build capacity because your reserve margin has gone down, right? Your demand has increased, your capacity has stayed the same, and your reserve margin is less than 15%, so you need to build some more. And it's also a big part of how a lot of other transmission planning requirements gets done as well. So the other thing I want to talk about besides weather, we talked about the main incorporation of uncertainty in load forecasting is weather. I also mentioned that there are other sources of uncertainty too. Climate's a really, really big one when you're thinking about what electricity demand is going to be like in the future. One of the encouraging parts of that is that actually temperature increases related to climate change are one of the more doable things to estimate, as opposed to changes in precipitation or sea level rise or other more complicated aspects of climate change. Temperatures are not as hard to predict, I don't think. Technology, the uptake or adoption of technology is incredibly hard to forecast, right? I mean, if you think about how badly telecommunications companies forecast the advent of the adoption of cell phones, right? A lot of people were sort of taken by surprise by that and were left sort of stranded in this business because of disruption. And I think there's a similar risk in energy technology as well. We do not have a good handle on, because of the possibility of innovation in the future, how technology is going to actually impact electricity demand. And the further out you go, 15 or 20 years, the more uncertain those are. Population growth and economic conditions are a little easier to predict, but maybe not on like multi-decade timescales either. And in some cases, is not what you need to when you're thinking about building new capacity to meet electricity demand in the near term. If you're only 5 years out, you should be okay. I think the challenge then becomes, once you build a power plant, you're good for 5. You're good in year 5, right? You built a new power plant to meet electricity demand. In year 6, it's really like over the lifetime of that power plant, over the next 30 or 40 years, you're exposed to all these different sources of uncertainty, and all of those have to go into load forecasting as well. So this is a pretty uncertain environment to be in. If you think about things from the utilities perspective, and I think it's useful to do that, this is a really high-risk environment, right? It requires massive investment of capital, billions of dollars, maybe even trillions of dollars overall. And our need for that investment is pretty uncertain out to the future, that can be a real challenge if there are not assurances in place that encourage utilities to make investments. If you're not guaranteeing in some way that they're able to recoup those capital costs over the long term, it makes them incredibly conservative. The flip side of that, of course, is that if you don't incorporate a lot of information, and I don't think I don't think there's a tendency on one side for utilities to invest in more, especially in places like North Carolina where utilities are regulated, and the market environment, whether it's a regulated state like North Carolina versus a deregulated wholesale market like PJM, matters a lot in terms of whether utilities have some guarantee in place that they're going to be able to recoup capital investments. I think so. In states like North Carolina, there's this sort of perverse incentive to just build more because there's this guarantee that they're going to recoup costs. In other places, that guarantee doesn't exist. But I think the risk in both cases is that you end up building potentially too much generation capacity, right? And if you build too much capacity and you have added redundancy in the system, there may be some benefits to that, right? You may decrease the likelihood of having some sort of outage out into the future. The downside is that you've taken out all these loans to build these power plants, and now you have this giant mortgage. And who pays that mortgage? It's the electricity customers, right? And so it turns out in some cases that the decisions to build power plants out into the future were based on forecasts of electricity demand that didn't end up holding up. And so an example of that is shown here. So this is what PJM, the peak demand forecast or load forecast in blue is, out through 22. But if you incorporate added energy efficiency forecasts, you can see that the peak load drops considerably, right? Especially as you go out into the future. And so the risk here is that you're making long-term planning decisions based on a bad forecast, and it may not lead to more system outages, but it leads to unnecessary system redundancy. If we're going to use energy efficiency more than we thought we would, we might build a power plant that we didn't need. And if we build a power plant that we don't need, then that cost is going to be spread out over customers unnecessarily, right? And so electricity prices will be higher. So here's an example for Duke Energy. This is a chart that was put out by, I think, NC Warren. And they're very strong proponents of environmental protection, and they're generally pretty antagonistic towards Duke Energy. So I don't know that this is a completely accurate graph, but I have seen lots of graphs that look something like this. And this is showing on the y-axis total energy sales, and on the all the black dots are, this is for Duke Energy Progress, so the eastern part of North Carolina, are all the projections that were made 10 years out of what Duke Energy thought that electricity demand was going to be. So the black dot that's 2005 is what Duke Energy in 2005 thought electricity demand in 2015 was going to be, right? And so the other thing to keep in mind here is the scale on the y-axis. So they're off, and they're off by quite a bit. But it's the red is not actually close to zero. It's actually close to 54,000. Anyway, the point is that Duke, at least on paper, overestimates what their electricity demand is going to be, right? Versus as opposed to what their actual demand has been, right? So why would Duke do this? Why would there be any systematic bias towards Duke overestimating load growth, right? I mean, it's a conservative viewpoint, And what they might tell you is that they want to be sure that they're planning for any increase in electricity demand, and they're erring on the side of building a little too much in order to prevent or lower the possibility that you have any sort of blackouts into the future. But this is a really controversial topic because the flip side of that, of course, is that they're just building power plants because they have a guaranteed, written into the law in North Carolina is an ability for Duke Energy to recover all those capital costs, right? So that if they, build a power plant and 50% of that cost is shareholder money, the shareholders now have a guaranteed legal right to increase electricity prices on customers, potentially, in order to earn their regulated 10% rate of return on that amount of money. So it's guaranteed profits. So that's why Duke, some people would suggest that Duke has this sort of perverse incentive to constantly build more stuff in order to, increase their revenue earnings, right? Their revenue earning potential. Okay, so upshot for this one, long-term predictions in this industry is really, really difficult, but it's a requirement. This is an industry where you have to make predictions out into the future. Even if you're going to be wrong, you have to make predictions because of how long it takes to build stuff. And the question as we move forward in this class, especially towards the end of the semester, we'll be thinking about how to make good decisions when we cannot get rid of uncertainty, right? If there is a distribution around all the decisions we make, and that's not a bad way to think about life in general, how do you make a good decision when it could go one way or the other, and you might think it goes right down the middle, it's the expected value, but you start to think about are you okay with going right down the middle and accepting the fact that it could be really bad? Or would you rather make a decision that, costs you more but eliminates some possibility that things are really bad, right? So we're going to start to think about more of this as we get towards decision making and stochastic modeling later on in the semester. All right, these are the references I use throughout. If at some point down the road you're interested in more load forecast type stuff and literature on that, PJM is probably the place to go to look for that. They have a lot of good documentation about exactly how they model things. All right, that's it. Thanks.